What if everything we think we know about the universe is just a sliver of the truth? What if our reality, with its familiar laws of physics, is just one thread in an infinite tapestry of possibilities? This isn't science fiction, it's the tantalizing idea at the heart of the multiverse theory. Across the scientific community, researchers are grappling with the mind-bending possibility that our universe might be just one of countless others, each operating under its own unique set of rules. Some universes might have stars and planets like ours, while others could be so alien that they defy our wildest imaginations. The implications of this idea stretch far beyond the realm of physics. It challenges the very foundations of philosophy, forcing us to rethink what it means to exist. If there are infinite universes, does that mean every possible version of you exists somewhere out there? Could there be a universe where gravity works backward or where time flows in reverse? These questions aren't just hypothetical, they're driving some of the most cutting-edge research in science today. In this video, we'll dive into the most striking models of the multiverse, from the bubble universes of inflationary cosmology to the parallel worlds of quantum mechanics. We'll explore how these theories are reshaping our understanding of reality and why they matter not just to scientists, but to anyone who's ever wondered about the true nature of existence. By the end, you'll see why the multiverse isn't just a wild idea. It's a puzzle that could unlock the deepest secrets of the cosmos. So, are you ready to step beyond the limits of our universe and explore what lies beyond? The idea of multiple universes isn't a product of modern science. It's a concept that has fascinated thinkers for centuries. Long before telescopes or particle accelerators, ancient philosophers pondered the possibility of worlds beyond our own. In ancient Greece, thinkers like Democritus speculated about an infinite cosmos filled with countless worlds, each with its own unique properties. Fast forward to the Renaissance, and figures like Giordano Bruno dared to suggest that the stars in the night sky might be suns with their own planets, hinting at the existence of realities far beyond our own. These early musings, though speculative, planted the seeds for what would later become the multiverse theory. It wasn't until the 20th century, however, that the multiverse idea began to take shape within the framework of modern science. The rise of quantum mechanics in the early 1900s forced physicists to confront the bizarre and counterintuitive nature of reality at the smallest scales. Among them was Hugh Everett, a young physicist who proposed the many worlds interpretation in 1957. Everett's groundbreaking idea suggested that every possible outcome of a quantum event actually happens, but in separate, branching universes. Imagine flipping a coin. In one universe, it lands on heads, while in another, it lands on tails. Both outcomes are real, just in different realities. This bold theory shook the foundations of physics and sparked heated debates that continue to this day. At the same time, cosmology was making its own strides toward the multiverse. The discovery of the Big Bang and the subsequent development of inflationary theory opened the door to the idea that our universe might not be alone. Inflation, the rapid expansion of space in the early moments of the cosmos, suggested that other regions of space could have expanded differently, creating bubble universes with their own distinct physical laws. Suddenly, the multiverse wasn't just a philosophical curiosity, it was a scientific possibility. These early ideas, from ancient philosophy to the radical theories of Everett and beyond, laid the groundwork for the diverse multiverse models we explore today. They remind us that the search for understanding is as old as humanity itself, and that sometimes the most profound truths begin as simple questions. What started as a spark of curiosity has now ignited a firestorm of scientific inquiry, pushing us to rethink not just our place in the universe, but the very nature of reality itself. And as we'll see next, the journey from these early ideas to today's cutting-edge theories is as fascinating as the multiverse itself. One of the most fascinating and controversial ideas in modern physics is the many worlds interpretation. Born from the strange and unpredictable world of quantum mechanics, this theory suggests that every tiny decision at the quantum level doesn't just have one outcome, it creates an entirely new universe. Think of it like this: every time a quantum particle has a choice, the universe splits. One path is taken here in our reality, while another path is taken in a parallel universe. It's as if reality is constantly branching, like a tree growing infinite new limbs. To understand this better, let's revisit a classic thought experiment, Schrödinger's cat. In this scenario, a cat is placed in a box with a device that has a 50-50 chance of releasing poison. According to quantum mechanics, until the box is opened, the cat exists in a superposition. It's both alive and dead at the same time. But the many worlds interpretation takes this a step further. It says that when the box is opened, the universe splits. In one reality, the cat is alive. In another, it's dead. Both outcomes are equally real, they just exist in separate, parallel worlds. This idea might sound like something out of a science fiction novel, but it's a serious proposal that attempts to explain the bizarre behavior of quantum particles. Traditional quantum mechanics tells us that particles can exist in multiple states at once, but it doesn't explain why or how those states collapse into a single outcome when observed. The many worlds interpretation offers an elegant solution. There's no collapse. Instead, every possible outcome happens, but each plays out in its own distinct universe. The implications of this are staggering. If every quantum decision spawns a new universe, then the number of parallel realities is unimaginably vast. There could be a universe where you made a different choice this morning, or one where the laws of physics themselves are completely different. This raises profound questions about the nature of reality. Are we just one version of ourselves among countless others? And if so, what does that mean for free will, identity, and even the concept of time? What's even more intriguing is how this model challenges our understanding of causality, the relationship between cause and effect. In the many worlds interpretation, cause and effect might not be as straightforward as we think. Every decision creates a new universe, meaning that the flow of events isn't a single, linear path but an ever-expanding web of possibilities. This idea forces us to rethink not just quantum mechanics, but the very fabric of how we perceive time and the unfolding of history. As we'll explore in the next section, this radical perspective doesn't just reshape our understanding of the universe, it invites us to question the fundamental nature of time itself. What if time isn't a river flowing in one direction, but a vast ocean of branching currents? The answers might be as strange as the questions themselves, and they'll take us even deeper into the mysteries of the multiverse. The bubble universe theory offers a strikingly different vision of the multiverse, one that feels almost poetic in its grandeur. Picture this: our universe isn't alone. It's just one bubble floating in an endless cosmic foam, each bubble a self-contained universe with its own unique laws of physics. This idea, rooted in the framework of inflationary cosmology, suggests that the rapid expansion of space in the early moments of the Big Bang didn't just create our universe, it spawned countless others, each inflating like bubbles in a vast, bubbling sea. Inflationary cosmology, first proposed in the 1980s, explains how the universe expanded exponentially in a fraction of a second after the Big Bang. This rapid stretching of space not only smoothed out the cosmos but also set the stage for the formation of galaxies and stars. But here's where it gets even more fascinating. Inflation might not have stopped everywhere at once. In some regions, space could have continued to expand, creating pockets that eventually became their own distinct universes. These bubble universes are like cosmic islands, each with its own physics constants and even dimensions. Some might have more gravity than ours, while others could have none at all. The possibilities are as vast as the multiverse itself, but how do we know any of this is more than just a compelling idea? The evidence lies in the cosmic microwave background radiation, the faint afterglow of the Big Bang. This ancient light, which fills the entire universe, carries subtle imprints of the early cosmos. Scientists have discovered tiny fluctuations in this radiation patterns that align with the predictions of inflationary theory. These fluctuations suggest that inflation did, in fact, happen, and if inflation happened, then bubble universes are a plausible consequence. It's like finding footprints in the sand and realizing they lead to an entire hidden world. The beauty of the bubble universe theory is that it doesn't just explain the origins of our universe, it opens the door to an infinite array of possibilities. Imagine a bubble where the fundamental forces are completely different, or one where matter behaves in ways we can't even comprehend. Some bubbles might be teeming with life, while others are barren and inhospitable. And here's the kicker, these bubbles aren't static. They're constantly forming, colliding, and even merging, creating a dynamic, ever-changing multiverse. This theory doesn't just challenge our understanding of the cosmos, it redefines it. If our universe is just one bubble among many, then the laws of physics we take for granted might not be universal at all. They could be local, specific to our little corner of existence. This raises profound questions about the nature of reality and our place within it. Are we the rule or the exception? And what would it mean to encounter a universe where the rules are entirely different? As we move forward, the bubble universe theory also connects seamlessly to another fascinating idea, the concept of parallel universes. If inflation can create bubble universes, could quantum mechanics create parallel ones? The connection between these two models isn't just theoretical, it's a bridge between the very large and the very small, showing how the multiverse might operate on multiple scales. And as we'll explore next, this interplay between cosmic and quantum realms could hold the key to unlocking the deepest mysteries of existence. What if somewhere out there, another version of you is living a life entirely different from your own? In a parallel universe, every choice you've ever made or didn't make could have led to a completely separate reality. This isn't just a wild thought experiment. It's a cornerstone of the parallel universe model, which suggests that infinite versions of reality exist simultaneously, each unfolding in its own unique way. Unlike the bubble universe theory, which focuses on distinct cosmic pockets, parallel universes propose that every possible outcome of every event is playing out somewhere, creating a vast tapestry of alternate realities. To grasp this idea, let's take a closer look at the simple act of making a decision. Imagine you're standing at a crossroads, deciding whether to turn left or right. In our familiar single reality view, you choose one path, and that's the end of the story. But in the parallel universe model, both choices happen. In one reality, you turn left, while in another, you turn right. Both versions of you are equally real, just existing in different timelines. This concept extends to every moment, every decision, and every quantum event, resulting in an infinite number of parallel worlds. This model doesn't just challenge our understanding of reality, it shatters it. If every possible outcome exists somewhere, then there's no single objective reality. Instead, reality becomes a kaleidoscope of possibilities, each one as valid as the next. Think about what that means for your own life. Somewhere out there, a version of you might have taken that job offer you turned down or pursued a passion you set aside. Another version might live in a world where history unfolded completely differently, where wars never happened, or where humanity discovered interstellar travel centuries ago. The implications of this are as profound as they are unsettling. It forces us to rethink not just the nature of existence, but also the very idea of identity. If there are infinite versions of you, which one is the real you? And if every decision creates a new universe, does that mean we have free will? Or are we simply following an infinite script written by the laws of physics? These questions blur the lines between science and philosophy, showing how deeply intertwined the two can be. What's even more fascinating is how this model connects to the many worlds interpretation of quantum mechanics. While the many worlds interpretation focuses on quantum events spawning new universes, the parallel universe model expands this idea to include every possible outcome, big or small. It's a cosmic dance of cause and effect, where every decision creates ripples that cascade into entirely new realities. As we continue to explore these ideas, one thing becomes clear. The multiverse isn't just a collection of separate worlds, it's a dynamic, interconnected web of possibilities. And while the parallel universe model pushes the boundaries of our imagination, it also raises questions that science is only beginning to answer. How do these infinite realities interact, if at all? And what does it mean for our understanding of time and space? These questions lead us to the next piece of the puzzle, the mathematical frameworks that make the multiverse theory possible. Behind every mind-bending idea lies a foundation of numbers and equations, and it's through these tools that scientists are working to turn speculation into understanding. So, as we prepare to dive into the equations and formulas that underpin the multiverse, remember, the journey into the unknown is just as important as the answers we hope to find. The multiverse isn't just a collection of wild ideas, it's a framework that scientists are actively working to understand. And when it comes to organizing these theories, few have done more to bring clarity than physicist Max Tegmark. Tegmark's groundbreaking classification of the multiverse into 4 levels offers a roadmap for navigating this vast and often bewildering landscape. Each level represents a different kind of multiverse, from the familiar to the utterly alien, and together they provide a comprehensive way to explore the possibilities. Let's start with level 1, the simplest and perhaps the most intuitive. This level suggests that our universe is just one of many within an infinite space. Imagine the cosmos as an endless ocean, with our universe as a single wave. Somewhere out there beyond the horizon, there could be other waves, other universes that are nearly identical to ours, differing only in small details. For example, in one of these universes, Earth might exist, but with a slightly different history. Maybe dinosaurs never went extinct, or humans evolved in a different way. The key idea here is that these parallel universes share the same fundamental laws of physics as ours. They're just separated by vast distances. This level is rooted in the idea of cosmic inflation, where space expanded so rapidly that regions of the universe became isolated from one another, creating distinct bubbles. Moving to level 2, things get a bit more exotic. Here, the multiverse isn't just about parallel universes within the same space, it's about universes with different physical constants. Picture a cosmic patchwork where each patch operates under its own unique rules. In one universe, gravity might be stronger, while in another, the speed of light could be slower. These variations arise from the idea that the initial conditions of the Big Bang weren't uniform, leading to different outcomes in different regions. This level is closely tied to the bubble universe theory, where each bubble represents a universe with its own distinct properties. What makes level 2 so fascinating is that it challenges the notion that the laws of physics are universal. Instead, they might be local, specific to each bubble. Now, let's dive into level 3, which takes us into the realm of quantum mechanics. This is where the many worlds interpretation comes into play. Every time a quantum event occurs, the universe splits, creating a new branch where each possible outcome happens. Think of it as a cosmic tree with infinite branches, each representing a different reality. In one branch, you might be reading this script, while in another, you're doing something entirely different. Level 3 suggests that all these branches are equally real, even if we can only experience one of them. This level blurs the line between the multiverse and our everyday lives, showing how even the smallest decisions could ripple out into entirely new realities. Finally, we arrive at level 4, the most abstract and mind-bending of them all. This level proposes that the multiverse isn't just about different physical laws or quantum outcomes, it's about entirely different mathematical structures. In other words, every possible mathematical universe exists somewhere. This means there could be universes governed by equations we haven't even discovered yet, with dimensions, forces, and realities that defy our current understanding. Level 4 challenges us to think beyond the limits of our imagination, suggesting that the multiverse might be more vast and varied than we can possibly comprehend. Tegmark's 4 levels provide a powerful framework for understanding the multiverse, from the familiar to the fantastical. They show us that the multiverse isn't just a single idea, it's a spectrum of possibilities, each with its own unique implications. And as we'll explore next, these models aren't just theoretical curiosities. They have profound implications for physics, from the nature of reality to the limits of scientific discovery. So, what do these multiverse theories mean for our understanding of the cosmos? The answers might just change everything we think we know. What if the laws of physics we take for granted aren't as universal as we think? For centuries, scientists have operated under the assumption that the fundamental constants of nature, like the speed of light, the strength of gravity, or the charge of an electron, are fixed and unchanging. These constants form the bedrock of our understanding of the universe, guiding everything from the motion of planets to the behavior of atoms. But multiverse theories turn this assumption on its head, suggesting that these so-called constants might not be so constant after all. In fact, they could vary dramatically from one universe to another, reshaping our understanding of reality itself. Take gravity, for example. In our universe, gravity is just strong enough to hold galaxies together, but not so strong that it collapses everything into a black hole. This delicate balance is often seen as a stroke of cosmic luck. But what if it's not luck at all? What if there are other universes where gravity is weaker, allowing stars to drift apart, or stronger, crushing matter into oblivion? This variation wouldn't just change the structure of the cosmos, it would redefine what's possible. Universes with stronger gravity might never form planets, while those with weaker gravity could lack the conditions for stars to ignite at all. The multiverse challenges us to think of physics not as a set of absolute rules, but as a menu of possibilities, each with its own consequences. This idea extends to other constants as well, like the speed of light. In our universe, light travels at about 300 million meters per second, a speed that seems unchangeable. But in the multiverse framework, this speed could be different elsewhere. Some universes might have light that moves faster, altering the very fabric of space and time, while others could have slower light, creating entirely unfamiliar forms of energy and matter. These variations could lead to universes where time flows differently, where causality breaks down, or where the very concept of distance becomes meaningless. As physicist Brian Greene puts it, the multiverse forces us to confront the possibility that the laws we've discovered might not be the only laws, they might just be the ones that work for us. What's even more striking is how these ideas challenge the notion of scientific determinism, the idea that the universe operates according to fixed, predictable rules. If the laws of physics can vary across universes, then the predictability we rely on in science might only apply within our own cosmic bubble. This doesn't mean science is wrong, it means it's incomplete. As cosmologist Laura Mersini-Horton explains, the multiverse isn't a rejection of science, it's an expansion. It's a reminder that the universe is far more complex and mysterious than we've ever imagined. These revolutionary ideas don't just change how we see the cosmos, they change how we see ourselves. If the laws of physics aren't universal, then our existence isn't just a product of chance. It's a product of a specific set of conditions that allowed life to emerge. This raises profound questions about our place in the multiverse. Are we the rule or the exception? And if there are other universes with different laws, could life exist there in forms we can't even imagine? As we grapple with these questions, it's clear that the multiverse isn't just reshaping physics, it's reshaping philosophy. What does it mean to exist in a reality where the rules aren't set in stone? How do we define truth, knowledge, or even reality itself? These are questions that go beyond the realm of science, touching on the deepest mysteries of existence. And as we'll explore next, the multiverse doesn't just challenge our understanding of the cosmos, it challenges our understanding of ourselves. What does it mean to exist in a multiverse? This question might sound abstract, but it strikes at the very heart of who we are and why we're here. Multiverse theories don't just challenge our understanding of physics, they force us to confront profound philosophical dilemmas about identity, purpose, and the nature of reality itself. If there are infinite universes, each with its own version of you, what does that mean for the idea of a singular self? Are you still you in a universe where your life took a completely different path? These aren't just thought experiments, they're questions that could redefine how we see ourselves and our place in the cosmos. Let's start with identity. In a single universe view, your sense of self feels solid and unchanging. You are the sum of your experiences, your memories, and the choices you've made. But in a multiverse, that narrative unravels. If every decision creates a new universe, then there are countless versions of you, each living a different life. In one reality, you might be a scientist, in another, an artist. Some versions might never have been born at all. This raises a haunting question: which one of these versions is the real you? Or is the very idea of a real self an illusion, a construct of our limited perspective? This idea doesn't just challenge our sense of identity, it shakes the foundations of purpose. If every possible outcome exists somewhere, does anything we do truly matter? In a multiverse, every choice is both made and unmade, every success and failure equally real. This might seem like a recipe for existential dread, but it can also be liberating. If our actions don't define a single, unchanging reality, then perhaps the meaning of life isn't about achieving some grand, universal purpose. Maybe it's about finding meaning in the here and now, in the choices we make and the lives we live, even if they're just one thread in an infinite tapestry. These questions don't just belong to philosophers, they're central to the scientific exploration of the multiverse. As physicist Sean Carroll puts it, the multiverse forces us to ask not just how the universe works, but why it works the way it does. Why do we live in a universe with laws that allow life to exist? Is it sheer luck, or is there something deeper at play? Some scientists suggest that the multiverse might provide an answer through the anthropic principle, the idea that we observe the universe the way it is because it's the only kind of universe that could support beings like us. In other words, we're here because this is one of the rare universes where life is possible. But does that mean our existence is inevitable, or is it just a cosmic coincidence? These philosophical debates don't just stay in the realm of theory, they spill over into the search for evidence. If the multiverse exists, how can we prove it? Can we ever observe these other universes, or are they forever beyond our reach? These questions aren't just academic, they're driving some of the most ambitious experiments in modern science. As we'll explore next, the quest to find evidence of the multiverse is pushing the boundaries of technology and imagination, challenging us to think bigger and dig deeper than ever before. And as we do, we're not just searching for answers about the cosmos, we're searching for answers about ourselves. Imagine trying to prove the existence of something you can't see, touch, or even detect directly. That's the monumental challenge scientists face when it comes to the multiverse. While the idea of parallel universes and cosmic bubbles is undeniably thrilling, the hard truth is that proving their existence requires more than just compelling theories. It demands evidence. And finding that evidence is no easy task. So how do researchers even begin to tackle such a profound mystery? The answer lies in the subtle clues left behind by the early universe and the cutting-edge tools we've developed to uncover them. One of the most promising avenues for multiverse research is the study of the cosmic microwave background, or CMB. This faint glow, often called the afterglow of the Big Bang, is the oldest light in the universe, and it holds a treasure trove of information about the cosmos' infancy. Scientists have already found tiny irregularities in the CMB, patterns that align with the predictions of inflationary theory, the idea that the universe expanded rapidly in its earliest moments. But could these irregularities also hint at the existence of other universes? Some researchers think so. They suggest that if our universe collided with another bubble universe in the distant past, it might have left a distinctive bruise or imprint in the CMB. Finding such a mark would be groundbreaking, but it's like searching for a single fingerprint on a vast cosmic canvas. The task is daunting, and so far, no definitive evidence has been found. Another intriguing possibility lies in the study of gravitational waves, ripples in space-time caused by cataclysmic events like black hole mergers or the Big Bang itself. These waves carry information about the universe's most violent moments, and some scientists believe they might also hold clues about the multiverse. For instance, if gravitational waves from the early universe show unexpected patterns, it could suggest interactions with other universes. The challenge here is that these waves are incredibly faint, and detecting them requires technology that pushes the limits of human ingenuity. Instruments like LIGO and future projects like the Laser Interferometer Space Antenna, or LISA, are designed to listen for these cosmic whispers, but even with their incredible sensitivity, the search is like trying to hear a pin drop in a thunderstorm. Of course, these methods come with their own set of challenges and controversies. Critics argue that the multiverse is inherently untestable, as other universes might be forever beyond our observational reach. After all, if these universes exist in separate regions of space or operate under different physical laws, how could we ever detect them? Some scientists even worry that the multiverse idea risks becoming a theory of everything and nothing, explaining everything but predicting nothing. It's a valid concern, and one that keeps researchers on their toes, constantly refining their methods and questioning their assumptions. Despite these hurdles, the search for evidence continues, driven by the tantalizing possibility that we might one day glimpse the true nature of reality. And while the tools we have now might not be enough, the future holds promise. Advances in technology, from more sensitive telescopes to new ways of analyzing data, could bring us closer to answering these profound questions. But even if we never find definitive proof, the journey itself is transformative. It forces us to think bigger, to question our assumptions, and to push the boundaries of what we thought was possible. As we look ahead, it's clear that the search for the multiverse isn't just about finding answers, it's about expanding our understanding of the cosmos and our place within it. And while the evidence remains elusive, the quest itself is reshaping science in ways we're only beginning to understand. So, what if the multiverse isn't something we can prove with a single experiment or observation? What if it's a puzzle that requires entirely new ways of thinking? In the next section, we'll explore how scientists are approaching this challenge from fresh angles, using creativity and imagination to unlock the secrets of the multiverse. The journey is far from over, and the discoveries ahead could change everything we thought we knew. What if the key to unlocking the multiverse lies not in the particles we can see, but in the vibrations of tiny, invisible strings? This is the bold idea at the heart of string theory, one of the most ambitious and controversial frameworks in modern physics. At its core, string theory proposes that the fundamental building blocks of the universe aren't point-like particles, as we've long assumed, but incredibly small, one-dimensional strings. These strings vibrate at different frequencies, much like the strings of a guitar, and these vibrations give rise to everything in the cosmos, from the smallest quark to the largest galaxy. But string theory doesn't stop there. It also suggests that these strings exist in a space with more than the 3 dimensions we're familiar with, up to 10 or even 11 dimensions, depending on the version of the theory. And hidden within these extra dimensions could be the key to understanding the multiverse. The idea of extra dimensions might sound like science fiction, but it's a central pillar of string theory. Imagine our universe as a sheet of paper. To a 2-dimensional being living on that sheet, everything exists in length and width. Height is unimaginable. But to us, as 3-dimensional beings, that extra dimension is obvious. String theory takes this concept further, proposing that there are additional dimensions curled up so tightly that we can't perceive them. These hidden dimensions could be home to other universes, each vibrating at its own unique frequency. In this view, the multiverse isn't just a collection of separate bubbles or branching timelines. It's a symphony of vibrating strings, each playing its own part in the cosmic orchestra. One of the most compelling aspects of string theory is its potential to unify the fundamental forces of nature. For decades, physicists have struggled to reconcile the 2 great pillars of modern physics: quantum mechanics, which governs the behavior of the very small, and general relativity, which describes the very large. String theory offers a tantalizing solution, suggesting that all forces, gravity, electromagnetism, and the strong and weak nuclear forces, are different manifestations of the same underlying phenomenon, vibrating strings. This unification could provide a framework for understanding not just our universe, but the entire multiverse. As physicist Brian Greene explains, string theory is like a master key, unlocking doors to realms we never knew existed. But for all its promise, string theory isn't without its challenges. One of the biggest criticisms is that it's incredibly difficult to test. The strings themselves are unimaginably small, far smaller than anything we can currently observe, and the extra dimensions they inhabit are equally elusive. This has led some critics to argue that string theory is more philosophy than science, a beautiful idea with no way to verify it. Others point out that string theory doesn't yet provide a unique prediction for the multiverse. Instead, it suggests a vast landscape of possible universes, each with its own set of physical laws. While this might explain why our universe has the constants it does, it also raises questions about predictability. If anything is possible, how do we know what's real? Despite these challenges, string theory remains one of the most promising paths to understanding the multiverse. It offers a way to think about reality that's both deeply mathematical and profoundly imaginative, pushing the boundaries of what we thought was possible. And as we'll explore next, it's not the only theory that challenges our understanding of the cosmos. The holographic principle, which suggests that our universe might be a projection of information stored on a distant boundary, takes these ideas even further, blending the worlds of physics and information theory in ways that could revolutionize our understanding of reality. So, as we prepare to dive into this next frontier, remember, the search for answers is as much about the questions we ask as the theories we create. What if everything we see, touch, and experience is nothing more than a projection, a cosmic hologram created by information encoded on a distant, two-dimensional surface? This is the mind-bending idea at the heart of the holographic principle, a theory that turns our understanding of reality upside down. Imagine the universe as a movie projected onto a screen. The images we see are vivid and three-dimensional, but the source of those images, the film itself, is flat and two-dimensional. In the same way, the holographic principle suggests that our three-dimensional reality might emerge from information stored on a two-dimensional boundary, like a cosmic DVD encoding the entire universe. This idea didn't come out of thin air. It emerged from the study of black holes, those enigmatic regions of space where gravity is so strong that not even light can escape. In the 1970s, physicist Jacob Bekenstein discovered that the surface area of a black hole's event horizon, the point of no return, holds a surprising amount of information. Later, physicist Leonard Susskind and others expanded on this idea, proposing that all the information about what falls into a black hole is stored on its surface, not inside it. This led to the radical notion that the universe itself might work the same way, with all the information about our three-dimensional reality encoded on a two-dimensional boundary. It's as if the universe is a hologram with depth and dimension emerging from flat, encoded data. The implications of this principle are staggering. If the holographic principle is correct, then space and time as we know them might not be fundamental. Instead, they could be emergent properties arising from the way information is processed and displayed. This challenges the very foundation of physics, suggesting that the fabric of reality might be more like a computer simulation than a fixed physical structure. It also raises profound questions about the nature of the multiverse. If our universe is a hologram, could other universes be holograms too, each encoded on its own boundary? And if so, what connects them? Are they separate projections, or do they share a deeper, hidden layer of reality? To grasp this concept, let's use a vivid metaphor. Think of the universe as a giant, cosmic smartphone. The screen displays a rich, interactive world: apps, images, videos, but all that information is stored in the phone's memory as binary code, ones and zeros. In the same way, the holographic principle suggests that the universe we experience is just the screen, while the real action happens in the code encoded on a lower dimensional surface. This idea doesn't just reshape our understanding of space and time, it blurs the line between the physical and the informational, showing how deeply intertwined they might be. The holographic principle doesn't just challenge traditional views of reality, it opens up entirely new ways of thinking about the multiverse. If our universe is a projection, then other universes might be projections too, each with its own unique code. This could mean that the multiverse isn't just a collection of separate worlds, but a network of holographic realities, each emerging from its own boundary. It's a vision of the cosmos that's as beautiful as it is baffling, and it's pushing scientists to rethink everything they thought they knew. But the holographic principle isn't the only theory that challenges our understanding of reality. What if our universe isn't just a hologram but a simulation? Could we be living in a universe created by an advanced civilization running on a cosmic supercomputer? It's a question that takes us into the realm of simulated universes, where the lines between science, philosophy, and science fiction blur. As we'll explore next, this idea isn't just a thought experiment. It's a serious scientific hypothesis that could revolutionize how we see ourselves and the cosmos. What if everything you know, your memories, your experiences, even the world around you, is nothing more than lines of code in an unimaginably advanced simulation? This isn't the plot of a sci-fi movie. It's a serious hypothesis that has gained traction among scientists and philosophers alike. Known as the simulation argument, it suggests that our universe might not be the base reality, but a virtual construct created by a highly advanced civilization. Think of it like this: if a future society could build simulations so realistic that the beings inside them believed they were real, what's to say we're not one of those simulations? The idea might sound far-fetched, but when you dig into the reasoning behind it, it's harder to dismiss than you might think. Let's start with the philosophical side of the argument. In 2003, philosopher Nick Bostrom published a paper that laid the groundwork for this theory. He proposed a trilemma. 1. Almost all civilizations at our level of technological development go extinct before they can create simulations. 2. Advanced civilizations lose interest in creating simulations. Or 3. We are almost certainly living in a simulation. Bostrom's reasoning is based on probability. If even a tiny fraction of civilizations survive long enough to create simulations, and if they decide to run them, the number of simulated minds could vastly outnumber the real ones. Statistically, the odds of us being in the base reality are slim. It's a chilling thought, but one that's hard to ignore when you consider the exponential growth of computing power and virtual reality technologies. But what about the science? Could there be any evidence to support this idea? Some researchers have suggested that if our universe is a simulation, there might be glitches or limitations in the code, tiny imperfections that reveal the underlying structure. For example, physicist Silas Bean proposed that if space-time is pixelated at the smallest scales, like a digital image, we might detect these pixels by studying high-energy particles. Others have looked for anomalies in the cosmic microwave background, the same ancient light that holds clues about the multiverse, searching for patterns that might hint at a programmed reality. So far, no definitive evidence has been found, but the search continues, driven by the tantalizing possibility that we might one day uncover the truth. The simulation hypothesis also resonates deeply with popular culture, which has long explored the idea of artificial realities. From The Matrix to Inception, stories about simulated worlds have captivated audiences, tapping into our deepest fears and curiosities. These films ask the same questions scientists and philosophers are grappling with. What is real? How do we know? And if we are living in a simulation, does it even matter? These cultural touchstones make the concept more relatable, but they also highlight the profound implications of the theory. If our reality is a construct, what does that mean for free will, morality, or even the nature of consciousness itself? Critics, of course, are quick to point out the flaws in the simulation argument. Some argue that it's untestable. If a simulation is perfect, how could we ever know we're in one? Others question the assumptions behind Bostrom's trilemma, suggesting that advanced civilizations might not have the motivation or resources to create such simulations. And then there's the philosophical objection. If we can't prove we're in a simulation, is the idea even worth considering? These are valid points, but they don't necessarily invalidate the argument. Instead, they remind us that the simulation hypothesis is as much about asking questions as it is about finding answers. What's fascinating about this idea is how it connects to the broader conversation about the multiverse. If our universe is a simulation, could other universes be simulations too? Could the multiverse itself be a kind of cosmic computer, running countless simulations in parallel? And if so, what role does consciousness play in all of this? These are questions that bridge the gap between the simulation argument and the mysteries of the multiverse, leading us into a deeper exploration of how mind and reality might be intertwined. As we'll see next, the role of consciousness in the multiverse is one of the most intriguing and controversial topics in modern science, challenging us to rethink not just the nature of the cosmos, but the nature of ourselves. What if the very act of observing the universe could change its reality? This startling idea lies at the heart of a theory that connects consciousness to the multiverse, blurring the line between observer and observed. For centuries, science has treated the universe as something separate from us, a vast, objective reality governed by fixed laws. But what if our minds aren't just passive witnesses to the cosmos? What if they're active participants shaping the very fabric of existence? This isn't just a philosophical musing. It's a serious scientific debate that challenges some of our most fundamental assumptions about reality. Let's start with quantum mechanics, the branch of physics that deals with the smallest building blocks of the universe. At this scale, particles don't behave like tiny billiard balls following predictable paths. Instead, they exist in a haze of probabilities, only settling into definite states when observed. This phenomenon, known as the observer effect, suggests that the act of measurement plays a crucial role in determining reality. But here's where it gets even more intriguing. Some interpretations of quantum mechanics, like the Copenhagen interpretation, propose that consciousness itself might be the key to this process. In other words, it's not just the tools we use to measure the universe that matter, it's the awareness behind them. Could our minds in some way be shaping the multiverse? This idea takes on even greater significance when we consider the role of consciousness in the many worlds interpretation of quantum mechanics. If every quantum decision spawns a new universe, then every act of observation could be creating an entirely new reality. Imagine you're looking at a quantum particle that can exist in two states at once. According to the many worlds interpretation, the moment you observe it, the universe splits. In one reality, you see the particle in state A, in another, state B. Both realities are equally real, but your consciousness only experiences one of them. This raises a profound question. Is consciousness the thread that ties these parallel realities together, or is it the force that unravels them? These theories don't just challenge our understanding of physics, they shake the foundations of philosophy and even our sense of self. If consciousness plays a role in shaping reality, then the boundaries between the observer and the observed begin to dissolve. Are we separate from the universe, or are we an integral part of it? And if consciousness is fundamental to the multiverse, what does that mean for other forms of awareness? Could there be universes where consciousness works differently, or where it doesn't exist at all? These questions push us to rethink not just the nature of reality, but our place within it. Of course, these ideas are far from universally accepted. Critics argue that linking consciousness to the multiverse risks veering into pseudoscience, as it's incredibly difficult to test or measure such claims. Others point out that the observer effect in quantum mechanics doesn't necessarily require consciousness. It could simply be the result of interaction between particles and measuring devices. Still, the possibility that our minds might influence the cosmos is too tantalizing to ignore, and it's a topic that continues to spark heated debates among scientists and philosophers alike. As we wrestle with these questions, one thing becomes clear. The connection between consciousness and the multiverse isn't just a scientific curiosity. It's a profound exploration of what it means to be human. It forces us to confront the possibility that our thoughts, our perceptions, and even our very existence might be woven into the fabric of the cosmos in ways we're only beginning to understand. And as we move forward, this exploration leads us to another pressing question. If we truly are shaping reality, what responsibilities come with that power? The ethical implications of these theories are as complex as they are fascinating, and they'll be the focus of our next discussion. What if one day we could step into another universe, not just observe it from afar, but interact with it, explore it, or even change it? This isn't just a sci-fi scenario, it's a question that scientists and ethicists are beginning to grapple with as multiverse theories evolve. The idea of accessing other universes opens up a Pandora's box of ethical dilemmas, forcing us to confront questions about responsibility, identity, and the potential consequences of meddling with realities beyond our own. If we could cross into another universe, would we have the right to do so? And if we did, what responsibilities would come with that power? Let's start with a thought experiment. Imagine you discover a universe where humanity's greatest mistakes never happened. A world where wars were avoided, diseases were eradicated, and the environment was preserved. It's a utopia, a shining example of what could have been. Now, imagine you have the ability to bring knowledge from that universe back to ours. You could share their solutions, learn from their successes, and potentially change the course of history. But here's the catch. What if your actions inadvertently disrupt their world? What if your interference, no matter how well-intentioned, leads to unforeseen consequences? This is the ethical tightrope we'd have to walk, balancing the desire to help with the risk of harm. The ethical challenges don't stop there. If we could interact with other universes, we'd also have to confront questions about identity and autonomy. Suppose you meet an alternate version of yourself in another universe. Are they truly you, or are they a separate individual with their own thoughts, feelings, and choices? If you make decisions that affect them, are you violating their autonomy? These questions become even more complex when considering universes with different moral frameworks. What if a universe operates under rules that seem unethical or even horrifying to us? Do we have the right to intervene, or would that be an act of cosmic imperialism, imposing our values on a reality that functions differently? Then there's the question of unintended consequences. Even small changes in one universe could ripple across the multiverse in ways we can't predict. Think about the butterfly effect, the idea that a tiny action in one place can lead to massive changes elsewhere. Now, imagine that effect playing out across infinite realities. A decision made in one universe could cascade into chaos in another, creating problems we never anticipated. This raises a profound ethical question. Do we have the right to take such risks, knowing the potential fallout, or should we adopt a hands-off approach, leaving other universes untouched? These ethical dilemmas aren't just theoretical, they're deeply tied to the future of multiverse research. As scientists push the boundaries of what's possible, they'll need to consider not just the science, but the moral implications of their discoveries. What happens if we develop the technology to detect or even interact with other universes? How do we ensure that this power is used responsibly? These are questions that will require collaboration between scientists, ethicists, and policymakers, as well as input from the broader public. After all, the multiverse isn't just a scientific concept, it's a shared frontier, one that belongs to all of humanity. As we look ahead, it's clear that the ethical challenges of the multiverse are as vast and complex as the multiverse itself. They force us to think not just about what we can do, but what we should do. And as we grapple with these questions, we're reminded that science isn't just about discovery, it's about responsibility. The journey into the multiverse isn't just a quest for knowledge, it's a test of our values, our wisdom, and our humanity. And as we prepare to explore the future of multiverse research, these ethical considerations will continue to shape the conversation. What breakthroughs lie ahead, and how will we navigate the challenges they bring? The answers to these questions might just define the next chapter in our understanding of the cosmos and ourselves. As we stand on the brink of a new era in cosmology, the tools and technologies at our disposal are more powerful than ever before. The James Webb Space Telescope, often hailed as the successor to Hubble, is poised to revolutionize our understanding of the cosmos. With its unprecedented ability to peer deep into the infrared spectrum, Webb could unveil secrets of the early universe that have remained hidden for billions of years. Imagine looking back to a time when the first galaxies were forming, or detecting the faint echoes of cosmic inflation, the rapid expansion that might have seeded the multiverse itself. This isn't just about seeing farther, it's about seeing differently, with the potential to uncover clues that could reshape our understanding of reality. But Webb is just the beginning. Across the globe, scientists are deploying a new generation of instruments designed to probe the deepest mysteries of the universe. Gravitational wave detectors like LIGO and the upcoming LISA mission aim to listen for the faint ripples in space-time caused by cataclysmic events, from black hole mergers to the birth of the universe itself. These waves could carry imprints of other universes, offering a glimpse into a multiverse that's been theorized but never observed. Meanwhile, particle accelerators like the Large Hadron Collider are pushing the boundaries of what we know about the fundamental forces and particles that make up reality. Could they uncover evidence of extra dimensions or exotic particles that hint at the existence of other universes? The possibilities are as thrilling as they are vast. What's equally exciting is the role of interdisciplinary collaboration in this quest. The study of the multiverse isn't just the domain of physicists. It's a field that draws on mathematics, computer science, philosophy, and even art. Mathematicians are developing new frameworks to describe the geometry of higher dimensions, while computer scientists are creating simulations to model the behavior of quantum systems and cosmic structures. Philosophers are grappling with the profound implications of a multiverse, asking questions about identity, purpose, and the nature of existence. And artists are helping us visualize these mind-bending ideas, turning abstract concepts into vivid, relatable images. Together, these diverse perspectives are driving the field forward, showing that the search for the multiverse is as much a human endeavor as it is a scientific one. As we look to the future, one thing is clear: the journey into the multiverse is far from over. With each new discovery, we're not just expanding our knowledge of the cosmos, we're redefining what it means to explore, to question, and to imagine. And while the answers we seek may still lie beyond our reach, the pursuit itself is transforming science in ways we're only beginning to understand. But the impact of multiverse theories isn't confined to laboratories and observatories. These ideas are seeping into our culture, reshaping how we see ourselves and our place in the universe. From blockbuster movies to best-selling novels, the multiverse is capturing our collective imagination, inviting us to dream bigger and think deeper. So, what happens when science meets culture? How are these theories influencing the stories we tell and the way we see the world? That's the question we'll explore next as we dive into the cultural ripple effects of the multiverse and how they're changing the way we think about everything from art to identity. The multiverse isn't just a playground for physicists, it's a source of endless inspiration for storytellers, artists, and dreamers. From the pages of science fiction novels to the big screen, the idea of multiple realities has captured our collective imagination, shaping how we think about identity, choice, and the nature of existence itself. Take Marvel's multiverse, for example. In films like Spider-Man, No Way Home, and Doctor Strange in the Multiverse of Madness, we see heroes and villains navigating an infinite web of alternate realities, each with its own version of characters we thought we knew. These stories aren't just entertaining, they're a reflection of our deepest questions. What if things had turned out differently? What if we could meet another version of ourselves? Marvel's multiverse taps into a universal curiosity, one that transcends science and resonates with something deeply human. But Marvel is far from the only storyteller to explore these ideas. Authors like Philip K. Dick have been wrestling with the nature of reality for decades. In novels like The Man in the High Castle, Dick imagines a world where the Axis powers won World War II, creating a chilling alternate history that forces readers to confront the fragility of the present. His work often blurs the line between reality and illusion, asking us to question what's real and why it matters. These stories aren't just thought experiments, they're mirrors reflecting our anxieties, hopes, and the endless possibilities of what could have been. And they remind us that the multiverse isn't just a scientific concept. It's a narrative tool, one that allows us to explore the infinite what-ifs of existence. The multiverse has also found its way into art, where it inspires creators to push the boundaries of imagination. Visual artists use the concept to craft surreal, mind-bending works that challenge our perception of space and time. Think of M.C. Escher's Impossible Staircases or Salvador Dali's Melting Clocks. These iconic pieces evoke the disorienting sense of a reality that's fluid, ever-changing, and full of hidden dimensions. In music, too, the multiverse has left its mark. Bands like Radiohead and Muse weave themes of alternate realities and fractured identities into their lyrics, creating soundscapes that feel both otherworldly and deeply personal. These artistic expressions show that the multiverse isn't just a scientific idea, it's a cultural phenomenon, one that speaks to our desire to explore the unknown and imagine the unimaginable. So why do these ideas resonate so deeply with us? Perhaps it's because they tap into something fundamental about the human experience. We all wonder about the paths not taken, the choices we didn't make, and the lives we might have lived. The multiverse offers a way to explore those questions, giving us permission to dream bigger and think beyond the limits of our reality. It's a reminder that life is full of possibilities, and that even the smallest decisions can lead to entirely different outcomes. In a world that often feels fixed and finite, the multiverse is a source of hope, curiosity, and endless fascination. But as much as these stories inspire us, they also invite us to question. If the multiverse is such a powerful idea, why do some scientists remain skeptical? What challenges do these theories face, and how can we separate compelling storytelling from rigorous science? These questions lead us to the next chapter of our exploration, where we'll dive into the role of skepticism in multiverse theories, and why asking tough questions is just as important as dreaming big. While the multiverse captivates our imagination, not everyone is convinced it belongs in the realm of science. Critics argue that these theories are more speculation than testable hypotheses, raising important questions about what counts as legitimate science. At the heart of this debate is a fundamental principle. For an idea to be scientific, it must be falsifiable, meaning there must be a way to prove it wrong. But how do you test the existence of universes that, by definition, lie beyond our observational reach? This is the crux of the skepticism surrounding multiverse theories, and it's a challenge that scientists are still grappling with. Physicist Paul Steinhardt, a vocal critic of the multiverse, puts it bluntly: if you can't test it, it's not science. He argues that by invoking an infinite number of universes, each with its own set of physical laws, multiverse theories risk explaining away any observation without making concrete predictions. It's like saying everything is possible somewhere, which, while philosophically intriguing, doesn't provide a clear framework for scientific inquiry. Critics like Steinhardt worry that this approach could undermine the rigor of physics, turning it into a speculative exercise rather than a discipline rooted in evidence. But proponents of the multiverse aren't backing down. They argue that while direct evidence may be elusive, there are indirect ways to test these theories. For example, if our universe collided with another bubble universe in the distant past, it might have left a distinctive imprint in the cosmic microwave background. Detecting such a mark would provide strong support for the multiverse concept. Similarly, anomalies in gravitational waves or the behavior of high-energy particles could hint at interactions with other universes or hidden dimensions. As physicist Sean Carroll points out, just because something is hard to test doesn't mean it's impossible. science has a history of finding clever ways to explore the seemingly unexplorable. Another response to the criticism is that the multiverse isn't a single, monolithic theory, it's a collection of ideas, some of which are more testable than others. For instance, the many worlds interpretation of quantum mechanics makes specific predictions about the behavior of particles, which can be tested in laboratory experiments. Similarly, inflationary cosmology, which underpins the bubble universe theory, has already been supported by observations of the cosmic microwave background. As physicist Max Tegmark explains, the multiverse isn't a free-for-all. It's a framework that emerges naturally from well-established theories, and those theories are testable. Still, the debate highlights a broader tension in science, the balance between bold, imaginative thinking and the need for empirical evidence. The multiverse pushes the boundaries of what we consider knowable, challenging scientists to think beyond the observable universe. But as physicist Brian Greene reminds us, science thrives on questions, not just answers. The multiverse forces us to ask questions we might never have considered otherwise, and that's a good thing. So where does this leave us? While the multiverse remains a controversial idea, it's clear that it's sparking important conversations about the nature of science and the limits of human understanding. Whether these theories ultimately prove true or not, they're pushing us to think bigger and dig deeper. And that's a hallmark of scientific progress. But as we move forward, it's worth considering whether there are other explanations for the cosmic phenomena that multiverse theories seek to explain. Could there be simpler, more elegant solutions to the mysteries of the universe? That's the question we'll explore next. What if the multiverse isn't the only way to explain the mysteries of the cosmos? While the idea of infinite universes is undeniably captivating, it's not the only game in town. Scientists have proposed several alternative theories that attempt to tackle the same questions without invoking the multiverse. These ideas, from modified gravity to cyclic cosmology, offer fresh perspectives on the universe's deepest puzzles, and they're just as fascinating in their own right. Let's take a closer look at some of these alternatives and see how they stack up. First up is the concept of modified gravity. For decades, our understanding of the universe has been built on Einstein's theory of general relativity, which describes gravity as the curvature of space-time. But as powerful as this theory is, it struggles to explain certain observations, like the way galaxies rotate or the accelerating expansion of the universe. To fill these gaps, some scientists have proposed tweaking gravity itself. One popular idea is modified Newtonian dynamics, or MUND, which suggests that gravity behaves differently on cosmic scales than it does in our everyday experience. Instead of invoking dark matter or dark energy, two mysterious substances that remain undetected, MUND proposes that we simply don't fully understand how gravity works. While this theory has its supporters, it hasn't yet been able to explain all the phenomena that general relativity can, leaving it as a compelling but incomplete alternative. Another intriguing idea is cyclic cosmology, which paints a very different picture of the universe's history. Instead of a single Big Bang marking the beginning of everything, cyclic models propose that the universe undergoes endless cycles of expansion and contraction. Imagine the cosmos as a cosmic accordion, breathing in and out over eons. Each cycle begins with a Big Bang, expands into a vast universe, and eventually collapses back into a singularity, only to start the process all over again. This idea elegantly sidesteps the need for a multiverse by suggesting that our universe is just one chapter in an infinite cosmic story. The challenge, however, is explaining how the universe transitions from collapse to rebirth without losing all its structure, a problem that cyclic models are still working to solve. Then there's the holographic principle, which we touched on earlier. This theory suggests that our three-dimensional universe might actually be a projection of information stored on a two-dimensional surface. It's a radical idea that challenges our understanding of space and time, but it also offers a way to explain certain cosmic phenomena without invoking the multiverse. For example, the holographic principle could provide insights into the nature of black holes or the fine-tuning of the universe's constants. While it's still a speculative theory, it's a reminder that there are many ways to approach the mysteries of the cosmos. Each of these alternatives has its strengths and weaknesses, and none have yet been able to fully replace the multiverse as a leading explanation for the universe's most puzzling features. But that's the beauty of science. It's a constant search for answers, with each new idea pushing us closer to the truth. And as we explore these theories, we're reminded that the multiverse isn't the only way to think about reality. Sometimes the most profound insights come from asking the simplest question: what if we're missing something? This brings us to another crucial piece of the puzzle: the role of mathematics in understanding the cosmos. Whether we're talking about the multiverse, modified gravity, or cyclic cosmology, math is the language that ties it all together. It's the tool that allows us to describe the universe, make predictions, and test our ideas. But as we'll see next, math isn't just a tool, it's a window into the very fabric of reality, offering glimpses of truths that go beyond what we can observe. So, what happens when we let the numbers lead the way? The answers might just change how we see everything. Mathematics has often been called the language of the universe, and for good reason. It's the tool that allows us to translate the cosmos into something we can understand, a bridge between the abstract and the tangible. From the orbits of planets to the behavior of subatomic particles, math provides the framework that makes sense of it all. But when it comes to the multiverse, mathematics takes on an even more profound role. It's not just a tool for understanding, it's a way of exploring realities that lie beyond our reach, a map to territories we can't yet see. Consider Einstein's theory of general relativity, one of the most elegant and powerful mathematical models ever devised. With a handful of equations, Einstein redefined gravity, showing how massive objects warp the fabric of space-time. His work didn't just explain the motion of planets, it predicted phenomena like black holes and gravitational waves, concepts that seemed almost fantastical at the time but were later confirmed by observation. This is the beauty of mathematics. It allows us to glimpse the unseen, to predict the unpredictable, and to test ideas that stretch the limits of imagination. And when it comes to the multiverse, it's no different. Whether we're modeling the expansion of bubble universes or calculating the probabilities of quantum outcomes, math is the lens through which we peer into the unknown. But mathematics isn't without its limitations. As powerful as it is, it's only as good as the assumptions we build into it. Take string theory, for example. This ambitious framework relies on complex equations to describe the universe in terms of tiny, vibrating strings. But for all its elegance, string theory has yet to make a testable prediction, leaving some to question whether it's truly scientific or just a beautiful set of equations. This tension between beauty and practicality is a recurring theme in the study of the multiverse. While math can help us imagine infinite realities, it can't always tell us which ones are real. Another challenge is the sheer complexity of the models themselves. As our understanding of the cosmos deepens, the mathematics required to describe it becomes increasingly abstract. Concepts like higher dimensions, quantum entanglement, and cosmic inflation push the boundaries of what's mathematically possible, often leading to equations that are as bewildering as they are insightful. This raises an important question. If a theory is so complex that only a handful of people can understand it, does it still have value? The answer, of course, is yes, but it also reminds us that math, for all its power, is a tool, not an end in itself. It's a way of asking questions, not just answering them. Despite these challenges, mathematics remains indispensable in our quest to understand the multiverse. It's the thread that ties together disparate ideas from the quantum to the cosmic, and it's the foundation on which all of modern physics is built. But as we continue to explore these cosmic mysteries, we're reminded that math is just one piece of the puzzle. There's another dimension to this story, one that goes beyond equations and experiments, a dimension that touches on the very nature of existence itself. This brings us to an intriguing question: what happens when science meets spirituality? Throughout history, the search for understanding has often blurred the lines between the two, with thinkers from Isaac Newton to Carl Sagan exploring the deeper meaning behind the numbers. In the next section, we'll dive into this fascinating intersection, examining how multiverse theories challenge not just our understanding of the cosmos, but our sense of purpose and connection to something greater. Are we alone in the multiverse, or is there something more? The answers might just surprise you. Throughout history, science and spirituality have often been seen as opposing forces, one rooted in logic and evidence, the other in faith and intuition. But when it comes to the multiverse, these two worlds collide in fascinating ways. The idea of infinite realities, each with its own set of laws and possibilities, echoes themes found in ancient spiritual traditions. From Hindu cosmology's concept of countless universes or lokas to Buddhist teachings on the impermanence and multiplicity of existence, the multiverse isn't just a modern scientific idea, it's a thread that weaves through humanity's deepest questions about the nature of reality. What if science and spirituality aren't as far apart as we think? What if they're simply different languages for describing the same profound mysteries? Consider the parallels. In quantum mechanics, particles exist in multiple states simultaneously until observed, a phenomenon that resonates with spiritual notions of interconnectedness and the power of perception. Some interpretations even suggest that consciousness plays a role in shaping reality, a concept that aligns with meditative practices aimed at transcending ordinary perception. And then there's the idea of unity. While science describes the multiverse as a vast, interconnected web of realities, many spiritual traditions speak of an underlying oneness that connects all things. Are these just coincidences, or do they point to a deeper truth about the nature of existence? These connections don't just challenge our assumptions, they invite us to think differently about the relationship between science and spirituality. For centuries, religion and science have often been at odds, with each claiming to hold the key to understanding the universe. But the multiverse blurs these boundaries, suggesting that both disciplines might be grappling with the same profound questions, just from different angles. As physicist Fritjof Capra famously noted in his book The Tao of Physics, there's a striking harmony between the insights of modern physics and the wisdom of ancient spiritual traditions. Both seek to understand the fundamental nature of reality, and both remind us that the universe is far more complex and more beautiful than we can ever fully comprehend. But what does this mean for us? If science and spirituality are two sides of the same coin, how should we navigate the space between them? Some argue that science provides the tools to explore the physical world, while spirituality offers a framework for understanding our place within it. Others see the multiverse as a bridge, a concept that allows us to reconcile the empirical with the existential. It's a reminder that the search for meaning isn't just about finding answers, it's about asking the right questions. And in a universe or multiverse as vast and mysterious as ours, those questions might just lead us to a deeper understanding of ourselves and the cosmos. As we reflect on these connections, one question naturally arises. If the multiverse is real, could life exist in other universes? Could there be beings, perhaps even civilizations, thriving in realities entirely different from our own? This isn't just a question for scientists, it's a question that touches on the very essence of what it means to be alive. And as we'll explore next, the possibility of life in other universes isn't just a scientific curiosity, it's a profound exploration of the potential for existence in all its forms. What if life isn't unique to our universe? What if, somewhere out there in the vast multiverse, other forms of existence thrive in realities so different from our own that they defy imagination? This isn't just a question for science fiction, it's a serious scientific inquiry that challenges us to rethink what life could look like beyond the boundaries of our own universe. If the multiverse is real, and if other universes operate under different physical laws, could life exist there too? The answer might just depend on how flexible the conditions for life truly are. Let's start with what we know. In our universe, life as we understand it depends on a delicate balance of physical constants, things like the strength of gravity, the charge of an electron, and the speed of light. These constants shape the way matter interacts, the way stars form, and the way planets develop. If gravity were slightly stronger, stars might burn out too quickly. If the charge of an electron were slightly different, atoms might not even form. This fine-tuning has led some scientists to wonder, is life only possible in a universe with constants like ours, or could it exist in universes with entirely different rules? To explore this, let's imagine a universe where the fundamental forces are weaker. In such a reality, stars might form more slowly, burning cooler and lasting longer. Planets could be larger, with thicker atmospheres and slower geological processes. Could life emerge in such a place? Perhaps, but it would likely look nothing like life on Earth. Instead of carbon-based organisms, we might find life forms built from entirely different elements, thriving in environments that would seem alien to us. Some scientists even speculate that in universes with stronger nuclear forces, silicon-based life could dominate, adapting to conditions that would be inhospitable to us. The point is, life might not need to follow the same rules everywhere. It could be as diverse as the universes themselves. But what about universes where the laws of physics are so different that life as we know it seems impossible? Imagine a reality where time flows backward or where space has more than 3 dimensions. Could life exist there? This is where things get truly speculative. Some theories suggest that consciousness itself might not be bound by the same physical constraints as matter. If that's the case, then life, or something like it, might exist in forms we can't even begin to imagine. As physicist Lee Smolin puts it, the multiverse challenges us to think beyond the limits of our own experience. If there are other universes, then the possibilities for life are as infinite as the multiverse itself. Of course, all of this raises a deeper question. What does it mean to be alive? Is life defined by the ability to grow, reproduce, and adapt as we see on Earth? Or could it take on entirely different forms, existing in ways that we can't yet comprehend? These questions don't just challenge our understanding of biology, they push us to think about the very nature of existence itself. And while we may never have definitive answers, the search itself is a reminder of how little we truly know about the cosmos. As we ponder the possibility of life in other universes, it's worth considering how this idea connects to the broader mysteries of the multiverse. If life can exist in countless forms across infinite realities, what does that mean for our own place in the cosmos? Are we an exception or just one thread in an unimaginably vast tapestry? These questions lead us to the next frontier of our exploration, the nature of time in the multiverse. Is time a constant, universal force, or does it flow differently in other realities? The answers might just change how we see everything, including ourselves. What if time, the steady rhythm that structures our lives, isn't as universal as it seems? In our universe, time marches forward in a linear fashion, from past to present to future. but in the multiverse, time might not play by the same rules. Imagine a universe where time flows backward, or one where it loops endlessly like a cosmic record stuck on repeat. These aren't just imaginative flights of fancy, they're serious possibilities that scientists are exploring, and they could completely reshape how we understand reality. Let's start with the concept of eternal inflation, a theory that suggests our universe is just one of countless bubbles in an endlessly expanding multiverse. In this framework, each bubble universe could have its own unique timeline, with time behaving in ways that seem alien to us. For instance, in some universes, time might not have a clear direction at all. Instead of flowing in a straight line, it could spiral, loop, or even branch into multiple paths. Picture a river that doesn't just flow downstream but splits into countless tributaries, each carving its own course through the landscape. In such a universe, the past, present, and future might not be distinct. They could all exist simultaneously, overlapping in ways that defy our everyday experience. This idea becomes even more intriguing when we consider the role of entropy, the measure of disorder in a system. In our universe, entropy increases over time, giving time its arrow, its one-way direction. But in other universes, entropy might behave differently. Imagine a universe where entropy decreases over time, causing events to unfold in reverse. In such a reality, a shattered glass might spontaneously reassemble itself, or a candle might burn brighter as it unburns. These scenarios might sound like science fiction, but they're grounded in the same physical principles that govern our own universe, just with a twist. Now, let's take this a step further. What if time itself is an emergent property, something that arises from the interactions of particles and forces rather than being a fundamental feature of reality? In some multiverse models, time might not exist at all in certain universes. Instead, these realities could be timeless with no past, present, or future, just a static, unchanging state. It's like a photograph capturing a single moment frozen forever. In such a universe, the concept of cause and effect would be meaningless, and the very idea of change would be foreign. These theories don't just challenge our understanding of time, they force us to rethink the nature of existence itself. If time isn't a universal constant but a variable that changes from universe to universe, what does that mean for our sense of self? How do we define identity in a multiverse where time might not even exist in some realities? These are questions that blur the line between physics and philosophy, showing just how profound the implications of the multiverse can be. But as we explore these mind-bending ideas, another question arises. What drives the multiverse to behave this way? What force, if any, governs the flow of time across infinite realities? This is where dark energy enters the picture, a mysterious force that's accelerating the expansion of our own universe. Could dark energy play a role in shaping the nature of time in other universes? The answers might just lie at the intersection of time, space, and the enigmatic fabric of the cosmos. So, as we prepare to dive into the mysteries of dark energy, remember, the multiverse isn't just a collection of alternate realities, it's a symphony of forces, each playing its part in the grand cosmic dance. What if the very force driving the expansion of our universe, dark energy, could also hold the key to understanding the multiverse? This mysterious energy, which makes up about 70% of the cosmos, is the invisible hand pushing galaxies apart at an accelerating rate. But here's the twist: dark energy isn't just shaping our universe, it might be shaping all universes, and if its properties vary across the multiverse, the implications are staggering. Some universes might expand so rapidly that stars and galaxies never form, while others could collapse back in on themselves, ending in a cosmic crunch. Dark energy isn't just a puzzle for cosmologists, it's a window into the infinite possibilities of the multiverse. To understand why dark energy is so crucial, let's start with what we know. In our universe, dark energy acts as a kind of anti-gravity, counteracting the pull of matter and driving the accelerated expansion of space. But what if this force isn't the same everywhere? In other universes, dark energy could be stronger, weaker, or even non-existent. These variations would have profound consequences. A universe with stronger dark energy might expand so quickly that matter can't clump together to form stars or planets. Imagine a cosmos that's nothing but a thin, cold soup of particles spreading endlessly into the void. On the other hand, a universe with weak or no dark energy might collapse under its own gravity, ending in a fiery big crunch. The multiverse, in this view, becomes a patchwork of realities, each with its own destiny shaped by the whims of dark energy. But why does dark energy behave the way it does? Physicist Sean Carroll puts it this way: dark energy is the most mysterious ingredient in the universe. It's not just a question of what it is, but why it has the value it does. In our universe, dark energy's strength is finely tuned, just enough to allow galaxies to form, but not so much that it tears everything apart. This delicate balance has led some scientists to suggest that dark energy's value might not be a coincidence. It could be a result of the multiverse's infinite variety, with our universe simply being one of the rare ones where life can exist. As physicist Laura Mersini-Horton explains, the multiverse offers a natural explanation for why dark energy has the value it does. It's a cosmic lottery, and we just happen to live in the winning ticket. The role of dark energy in the multiverse isn't just a theoretical curiosity, it's a question with real-world implications. Understanding how dark energy behaves across different universes could help us unravel the ultimate fate of our own cosmos. Will it continue expanding forever, eventually fading into cold, dark emptiness? Or could dark energy's grip weaken, leading to a dramatic collapse? These aren't just questions for scientists, they're questions that touch on the very meaning of existence. If the multiverse is real, then our universe's fate is just one thread in an infinite tapestry of possibilities. As we grapple with these mysteries, one thing becomes clear: dark energy isn't just a force, it's a story. It's the story of how the cosmos evolves, how universes are born and die, and how the multiverse weaves its infinite possibilities. And while we may not yet have all the answers, the search itself is transforming how we see the universe and our place within it. But dark energy isn't the only force shaping the multiverse. There's another, equally mysterious player in this cosmic drama: entropy, the measure of disorder in a system. In our universe, entropy increases over time, giving time its arrow and shaping the flow of events. But what happens when we zoom out to the scale of the multiverse? Could entropy behave differently in other realities, creating universes where time flows backward or loops endlessly? These are the questions we'll explore next as we dive into the enigmatic role of entropy in the multiverse, and how it might redefine our understanding of time itself. What if the arrow of time, the steady march from past to future that defines our lives, isn't a universal constant? In our universe, time flows in one direction because of entropy, the tendency for systems to move from order to disorder. A shattered glass doesn't spontaneously reassemble itself. A hot cup of coffee cools down rather than heating up. But what happens when we step into the multiverse? Could entropy behave differently in other realities, creating universes where time flows backward or even loops endlessly? These aren't just abstract musings, they're questions that challenge our deepest assumptions about the nature of existence. To understand entropy's role in the multiverse, let's start with a familiar thought experiment. Imagine a deck of cards perfectly ordered by suit and number. Shuffle it once and the order breaks down. Keep shuffling and the deck becomes more and more disordered. This is entropy in action, the natural progression from order to chaos. In our universe, this tendency gives time its direction, its arrow. But what if the rules were different elsewhere? In a universe where entropy decreases over time, the deck of cards might spontaneously reorder itself, with the shuffled deck returning to its original, pristine state. Time in such a universe wouldn't flow forward, it would flow backward, unraveling events rather than building them. Now, let's take this a step further. Imagine a universe where entropy isn't just reversed but fluctuates unpredictably. In this reality, time might not have a clear direction at all. Instead of a steady arrow, it could zigzag, loop, or even branch into multiple timelines. Picture a river that doesn't just flow downstream but splits into countless tributaries, each carving its own path through the landscape. In such a universe, the past, present, and future might exist simultaneously, overlapping in ways that defy our everyday experience. It's a mind-bending concept, but one that highlights just how fluid the nature of time could be across the multiverse. The implications of this are profound. If entropy behaves differently in other universes, it could mean that the very structure of reality, the way cause and effect operate, isn't fixed. In a universe where time flows backward, a broken glass might reassemble itself, but what would that mean for the people living there? Would they remember the future and forget the past? Would their lives unfold in reverse, with actions undoing themselves rather than building toward something new? These questions aren't just theoretical. They push us to rethink the nature of identity, memory, and even free will. But entropy doesn't just shape the flow of time, it also determines the ultimate fate of the cosmos. In our universe, entropy is steadily increasing, leading to what physicists call the heat death, a state where all energy is evenly distributed and no work can be done. It's a cold, dark end to the story, but in other universes, entropy might not follow the same path. A universe with weaker entropy could avoid heat death entirely, sustaining itself in a state of perpetual activity. On the other hand, a universe with stronger entropy might collapse into chaos much faster, ending in a fiery implosion rather than a slow fade. These possibilities remind us that the multiverse isn't just a collection of alternate realities, it's a spectrum of destinies, each shaped by its own unique rules. As we ponder these ideas, it's worth asking, what connects entropy to the broader mysteries of the multiverse? One intriguing possibility lies in the role of black holes. These enigmatic objects, where gravity is so strong that not even light can escape, are also thought to be engines of entropy. In fact, some theories suggest that black holes could be gateways to other universes, their intense gravitational fields bending the fabric of reality and creating pathways to entirely different realms. Could black holes hold the key to understanding how entropy operates across the multiverse? The answer might just lie at the intersection of time, space, and the enigmatic forces that shape existence itself. So, as we prepare to dive into the mysteries of black holes and their role in multiverse theories, remember, the story of entropy isn't just about the arrow of time, it's about the infinite possibilities that lie beyond. And in a multiverse as vast and varied as ours, those possibilities might just be limitless. Black holes have long been the ultimate cosmic enigmas, regions of space where gravity is so intense that nothing, not even light, can escape. But what if these mysterious objects are more than just cosmic vacuum cleaners? What if they're gateways to other universes, bridges connecting our reality to entirely different realms? This idea isn't just the stuff of science fiction. It's a serious scientific hypothesis that challenges our understanding of space-time and the very fabric of existence. At the heart of this theory lies the concept of the singularity, the point at the center of a black hole where the laws of physics as we know them break down. Traditional physics tells us that gravity becomes infinitely strong at the singularity, crushing matter into an infinitely dense point. But some physicists propose that this breakdown might not be the end of the story. Instead, the singularity could act as a kind of cosmic tunnel, a wormhole that connects our universe to another. Imagine a black hole not as a dead end, but as a doorway, a portal to a parallel reality where the rules of physics might be completely different. The science behind this idea is as fascinating as it is complex. According to Einstein's theory of general relativity, black holes warp space-time so severely that they create a funnel-like distortion. In some models, this distortion could theoretically connect two distant points in space-time, forming a bridge known as an Einstein-Rosen bridge or wormhole. While these wormholes are typically thought to be unstable and short-lived, some theories suggest that quantum effects, those strange, counterintuitive behaviors at the smallest scales, might stabilize them, making them viable pathways to other universes. But here's where it gets even more intriguing. If black holes are indeed portals, what happens to the matter that falls into them? Some scientists speculate that instead of being destroyed, this matter could be recycled into another universe, emerging as energy or even new matter on the other side. It's like tossing a stone into a pond and watching the ripples spread, except in this case, the ripples could be the birth of an entirely new reality. Of course, these ideas come with their fair share of challenges. For one, we can't directly observe what happens inside a black hole, let alone test whether they lead to other universes. The extreme conditions at the singularity make it nearly impossible for anything, even information, to escape. But despite these obstacles, the idea of black holes as gateways continues to captivate scientists and dreamers alike. It's a reminder that the universe is full of mysteries waiting to be unraveled, and that the boundaries of what we think is possible are constantly being pushed. The implications of this theory are as vast as the multiverse itself. If black holes are indeed portals, they could provide a way to explore other realities, offering glimpses into universes with different laws of physics, different histories, and even different forms of life. They could also help us understand the deeper connections between space, time, and the fundamental forces that shape the cosmos. But perhaps most importantly, they remind us that the universe is far stranger and more interconnected than we ever imagined. As we continue to explore these mind-bending ideas, another fascinating concept awaits us: quantum entanglement. Often described as spooky action at a distance, this phenomenon suggests that particles can be instantaneously connected across vast distances, defying our traditional understanding of space and time. Could this strange behavior hold the key to understanding how the multiverse operates? That's the question we'll dive into next as we explore the mysterious world of quantum entanglement and its potential role in the grand cosmic puzzle. Quantum entanglement is one of the most bizarre and fascinating phenomena in physics, often described as spooky action at a distance. It's the idea that two particles can become so deeply linked that the state of one instantly influences the state of the other, no matter how far apart they are. This connection defies our everyday understanding of space and time, suggesting that the universe operates in ways that are far stranger than we can imagine. But what if this entanglement isn't limited to particles within our universe? What if it extends across the multiverse, creating invisible threads that connect entirely different realities? This idea isn't just science fiction, it's a serious scientific hypothesis that could reshape our understanding of the cosmos. To grasp how quantum entanglement might work across universes, let's start with the basics. When two particles become entangled, they share a quantum state, meaning their properties are interdependent. Measure one particle, and the other's properties instantly align, even if they're light years apart. Albert Einstein famously called this spooky, because it seems to violate the speed of light, the cosmic speed limit. But quantum mechanics tells us that entanglement doesn't involve traditional communication. It's a fundamental feature of reality itself. Now imagine this phenomenon on a multiversal scale. If particles in our universe can be entangled, could particles in different universes also share this mysterious connection? Some physicists believe the answer is yes, suggesting that entanglement might weave a cosmic web that links universes together. The implications of this are staggering. If entanglement connects universes, it could provide a way for information to travel between them. Think of it as a cosmic Morse code, with particles in one universe influencing those in another to transmit messages across the multiverse. This idea opens up mind-bending possibilities for communication. Could civilizations in different universes use entanglement to send signals to one another? It's a tantalizing thought, but one that comes with enormous challenges. For one, entangled particles are incredibly fragile. Any interaction with their environment can break the connection. And even if entanglement does span universes, decoding the information it carries would require technology far beyond our current capabilities. Still, the idea that entanglement could bridge realities is a reminder of just how interconnected the multiverse might be. Expert insights add even more depth to this concept. Physicist Juan Maldacena, a pioneer in string theory and quantum gravity, has explored how entanglement might connect universes through the fabric of space-time. His work suggests that entanglement could be the glue that holds the multiverse together, creating a network of invisible links that bind different realities. This idea aligns with the holographic principle, which proposes that the information in our universe might be encoded on a two-dimensional surface, like a cosmic hologram. If entanglement connects these surfaces across universes, it could mean that the multiverse is far more unified than we've ever imagined. But entanglement's role in the multiverse doesn't stop at communication. It could also help explain some of the deepest mysteries of quantum mechanics, like the nature of wave-particle duality and the collapse of the quantum wave function. If entanglement operates across universes, it might provide a framework for understanding how particles can exist in multiple states at once until they're observed. This could mean that the act of observation in one universe influences the state of particles in another, creating a feedback loop that shapes the behavior of reality itself. It's a dizzying idea, but one that highlights just how deeply intertwined the multiverse might be. As we explore these possibilities, it's worth considering how entanglement might connect to another fundamental concept in physics: symmetry. Symmetry is the idea that the laws of physics remain the same under certain transformations, like rotating an object or flipping it in a mirror. It's a cornerstone of modern physics, shaping everything from the structure of atoms to the behavior of galaxies. But what role does symmetry play in the multiverse? Could it be the underlying principle that governs how universes interact or even how they're created? These are the questions we'll dive into next as we explore the mysterious and beautiful role of symmetry in the multiverse, a concept that might just hold the key to understanding the grand design of existence itself. Symmetry is often described as the hidden language of the universe, a principle that shapes everything from the tiniest particles to the vast expanse of galaxies. It's the idea that certain properties remain unchanged even when we rotate, flip, or transform them in some way. Think of a snowflake. No matter how you turn it, its intricate patterns look the same. But what if symmetry isn't just a feature of our universe? What if it's the glue that holds the multiverse together? In this section, we'll explore how symmetry might shape the laws of physics across different realities and why breaking that symmetry could lead to universes with entirely different rules. Let's start with an example from particle physics where symmetry plays a starring role. In the standard model of particle physics, symmetry helps explain why particles behave the way they do. Take the Higgs boson, the particle responsible for giving other particles mass. The discovery of the Higgs was a triumph of symmetry, but here's the twist. The Higgs field breaks a fundamental symmetry in the early universe. Before the Higgs field settled into its current state, particles like electrons and quarks had no mass. But as the universe cooled, the Higgs field froze into place, breaking the symmetry and giving particles their mass. This process, known as spontaneous symmetry breaking, is like a pencil balancing on its tip. It's perfectly symmetrical until it falls, choosing one direction over another. In the multiverse, this kind of symmetry breaking could happen in countless ways, leading to universes where particles have different masses, or where forces like gravity or electromagnetism operate under entirely different rules. Now, imagine a universe where symmetry breaking didn't happen at all. Without the Higgs field, particles would remain massless, and atoms as we know them might never form. On the other hand, in a universe where symmetry breaking happened more dramatically, particles could have much stronger interactions, creating a reality where stars burn brighter and hotter, or where black holes form more easily. These variations aren't just hypothetical, they're possibilities that arise naturally when we consider how symmetry shapes the fabric of existence. As physicist Frank Wilczek puts it, symmetry is not just a property of the universe, it's a principle that governs it, a hidden order that underlies the chaos we see. But symmetry isn't just about particles and forces, it's also about the structure of space and time. In our universe, the laws of physics are the same in every direction, a symmetry known as isotropy. But what if other universes aren't so uniform? Imagine a reality where space is warped or where time flows differently in different regions. These asymmetries could create universes that look and behave nothing like our own, with strange geometries and unfamiliar laws. It's a reminder that symmetry isn't just a mathematical curiosity, it's a fundamental force that shapes the very nature of reality. As we peel back the layers of symmetry in the multiverse, one question naturally arises: what happens when symmetry isn't just broken but absent altogether? Could there be universes where symmetry plays no role, where chaos reigns and order is an alien concept? These are questions that push the boundaries of our imagination, showing just how diverse and unpredictable the multiverse could be. And as we move forward, they lead us to an even more profound mystery, the concept of infinity. What does it mean for the multiverse to be infinite, and how does infinity shape the nature of reality itself? That's the puzzle we'll tackle next as we dive into one of the most mind-bending ideas in all of science. What does it mean for something to be infinite? It's a concept that stretches the limits of human imagination, a word that evokes both awe and unease. Infinity is more than just a number. It's a gateway to the boundless, a reminder that the universe might not have edges, beginnings, or ends. But when we apply this idea to the multiverse, things get even more mind-boggling. If the multiverse is infinite, then the possibilities within it are truly limitless. Every conceivable reality, every possible version of you, and every variation of the laws of physics could exist somewhere in this vast cosmic expanse. But with infinity comes a host of challenges, both mathematical and philosophical, that force us to rethink what we know about existence itself. Let's start with the mathematics. Infinity isn't just a big number, it's a concept that defies traditional arithmetic. You can't add to it, subtract from it, or divide it. It simply is. This makes infinity a powerful tool for describing the multiverse, but it also creates paradoxes that challenge our understanding. For example, in an infinite multiverse, there would be an infinite number of Earths, each with its own history and inhabitants. Somewhere out there, a version of you might be living a life identical to yours, while another version might be doing something completely different. But here's the twist. In an infinite multiverse, every possible scenario must exist somewhere, no matter how unlikely. This raises a perplexing question. If everything possible exists, does that mean nothing is truly unique? Or is uniqueness itself an illusion in an infinite sea of possibilities? The philosophical implications are just as profound. If the multiverse is infinite, then our existence becomes both extraordinary and mundane. On one hand, we're a product of an infinite number of cosmic dice rolls, a rare combination of events that allowed life to emerge. On the other hand, in an infinite multiverse, life like ours isn't rare at all, it's inevitable. This duality forces us to confront questions about purpose and meaning. If there are infinite versions of us, does that make our choices less significant? Or does it amplify their importance, knowing that every decision we make creates an entirely new reality? These are questions that blur the line between science and philosophy, showing how deeply intertwined the two can be. But infinity isn't just a philosophical puzzle, it's a scientific challenge. How do we study something that has no boundaries, no end points, and no limits? Traditional scientific methods rely on observation and measurement, but how do you measure the infinite? Some physicists argue that infinity might not even be a physical reality, but rather a mathematical convenience, a way to describe systems that are too vast or complex to comprehend. Others suggest that infinity could be a fundamental property of the multiverse, woven into its very fabric. As physicist Brian Greene puts it, infinity isn't just a big number. It's a way of thinking about the universe that pushes us to confront the limits of our understanding. So, what does infinity mean for the multiverse? It's a question that invites us to dream bigger and think deeper, to imagine a cosmos where the boundaries of reality are constantly expanding. But it also reminds us of the delicate balance between order and chaos. In an infinite multiverse, chance plays a starring role, shaping the fabric of existence in ways we're only beginning to understand. And as we explore this interplay between infinity and chance, we're led to the next chapter of our journey, the role of randomness in the multiverse and how it shapes the infinite tapestry of realities. What if chance isn't just a byproduct of the multiverse, but its very foundation? The answers might just change how we see everything, including ourselves. What if every decision, every event, and every moment in your life isn't just a single thread in the fabric of reality, but one of countless possibilities playing out across an infinite multiverse? This is the essence of chance in the multiverse, a cosmic lottery where every possible outcome exists somewhere, no matter how unlikely. In this framework, chance isn't just a random fluke, it's the driving force behind the infinite diversity of realities. But how does this work, and what does it mean for our understanding of existence? Let's roll the cosmic dice and explore how probability shapes the multiverse. Imagine buying a lottery ticket. In your universe, the odds of winning are astronomically low, but in the multiverse, every possible combination of numbers has been drawn somewhere. In one universe, you're a millionaire. In another, you're still scratching off tickets in hopes of a win. This isn't just a fun thought experiment, it's a way to visualize how chance operates on a universal scale. Every quantum event, every decision, every twist of fate creates a branching path, leading to realities where all possible outcomes are realized. It's as if the multiverse is a vast casino, with every roll of the dice spinning off new worlds. But chance in the multiverse isn't just about splitting universes, it's also about the fine-tuning of physical constants. Take gravity, for example. In our universe, gravity is just strong enough to hold galaxies together, but not so strong that it crushes everything into black holes. This delicate balance is often seen as a stroke of luck, but in the multiverse, it's just one possibility among infinite others. Some universes might have gravity so weak that matter drifts apart, while others might have gravity so strong that stars collapse before they can even form. The laws of physics themselves become a kind of cosmic roulette wheel, spinning out universes with every conceivable set of rules. This raises a fascinating question. If every possible outcome exists somewhere, does that make chance meaningless? In a way, yes, but in another way, it amplifies its significance. While the multiverse ensures that all possibilities are realized, the choices we make still matter, because they define the reality we experience. It's like being handed a deck of cards with every possible hand. You might not control which cards you draw, but how you play them is entirely up to you. This duality between the infinite possibilities of the multiverse and the finite choices of our own lives is one of the most profound implications of chance in the multiverse. So, what does this mean for our understanding of causality, the relationship between cause and effect? If every possible outcome exists, does that mean cause and effect are just illusions, or do they still hold meaning? These are the questions we'll explore next as we dive into the role of causality in the multiverse and how it shapes the infinite tapestry of realities. The answers might just change how we see everything, from the choices we make to the very nature of existence itself. In our everyday lives, cause and effect seem straightforward. A domino falls, knocking over the next one in line. But what if, in another universe, the dominoes could fall backward, or the line of cause and effect could twist into a tangled web? This is the puzzle of causality in the multiverse, where the rules of what causes what might not be as clear-cut as they seem in our reality. In some universes, time could flow backward, making effects precede causes. In others, causality might be so scrambled that events appear completely random. These aren't just wild ideas, they're serious scientific possibilities that challenge our deepest assumptions about how the universe works. Take, for example, a universe where time runs in reverse. In such a reality, you might see a shattered glass spontaneously reassemble itself, or a candle burn brighter as it unburns. Here, the effect, the intact glass or the unburned candle, happens before the cause, turning our understanding of causality on its head. This isn't just a quirky thought experiment, it's a scenario grounded in the laws of physics. If entropy, the measure of disorder, decreases over time in this universe, then events would naturally unfold in reverse order. The implications are staggering: a world where the future influences the past, and where actions have consequences that ripple backward through time. But what if causality doesn't just reverse? What if it disappears altogether? Imagine a universe where cause and effect are completely decoupled, where events occur without any clear connection to what came before. In such a reality, the very concept of a cause might be meaningless. This idea isn't as far-fetched as it sounds. In quantum mechanics, particles can exist in a state of superposition, where multiple outcomes are possible until an observation is made. In a universe where quantum effects dominate, causality might be so fluid that the line between cause and effect blurs into a haze of probabilities. It's a world where predictability breaks down, and the very fabric of reality becomes a playground of chance. These ideas aren't just abstract musings, they have real implications for how we understand the multiverse. If causality can vary so dramatically across different universes, what does that mean for our own reality? Could the laws of cause and effect we take for granted be just one possibility among many? And if so, how do we reconcile this with our need to make sense of the world around us? These questions push us to rethink not just the nature of causality, but the very foundations of how we perceive order and meaning in the cosmos. As we untangle the web of causality in the multiverse, it's worth considering how these ideas connect to another fundamental concept: information. In our universe, information is the glue that holds reality together, encoding the relationships between cause and effect. But in a multiverse where causality behaves differently, how does information function? Could it flow backward, loop endlessly, or even exist outside the bounds of time and space? These are the questions we'll explore next as we delve into the enigmatic role of information in the multiverse, a topic that might just change how we see everything from the smallest particles to the vast expanse of existence itself. What if the universe isn't made of matter or energy, but of something far more fundamental: information? Imagine the cosmos as a giant computer where every star, every atom, and even every thought is encoded in a vast, intricate network of data. This might sound like a scene from a sci-fi movie, but it's a serious scientific hypothesis gaining traction among physicists. Information isn't just a way to describe reality, it might be reality, the very fabric from which the multiverse is woven. In this section, we'll explore how information shapes the multiverse and why some experts believe it's the ultimate currency of existence. Let's start with a simple question: what is information? At its core, information is a measure of order, a way to distinguish one state from another. Think of it as the difference between a shuffled deck of cards and one neatly arranged by suit and number. That difference, the arrangement of the cards, is information. Now, apply this idea to the universe. Every particle, every force, every interaction can be thought of as a piece of information, a bit of data in the cosmic code. Physicist John Archibald Wheeler famously summed this up with the phrase, "it from bit." In other words, every particle, every force comes from a bit, a piece of information. It's a radical idea, but one that's reshaping how we understand reality. But how does this apply to the multiverse? If information is the building block of reality, then the multiverse could be seen as an infinite library, with each universe representing a unique set of data. Some universes might be filled with information that creates stars and galaxies, while others could be barren, with data patterns that don't allow for complex structures. This idea aligns with the holographic principle, which suggests that all the information in our universe might be encoded on a two-dimensional surface, like a cosmic hard drive. If this is true, then the multiverse could be a collection of interconnected holograms, each projecting its own unique reality. The implications of this are profound. If information is fundamental, then the laws of physics aren't just rules, they're algorithms, sets of instructions that determine how information is processed and displayed. This means that the multiverse might not be governed by randomness or chance, but by a deeper, underlying logic. As physicist Seth Lloyd puts it, the universe isn't just a computer, it's a quantum computer processing information at the most fundamental level. In this view, reality is a computation, a grand cosmic program running on the hardware of space-time. But if information is the foundation of reality, what does that mean for us? Are we, too, just patterns of information, complex arrangements of data in the cosmic code? Some scientists suggest that consciousness itself might be a form of information processing, a way for the universe to observe and interact with itself. This idea, while speculative, opens up fascinating possibilities about the nature of existence. Could consciousness be the link that connects us to the multiverse, allowing us to perceive and influence other realities? It's a question that blurs the line between science and philosophy, showing how deeply intertwined the two can be. As we explore these ideas, it's worth considering how information connects to another key concept: emergence. Emergence is the idea that complex systems can arise from simple rules, like how a flock of birds forms intricate patterns from the actions of individual birds. In the multiverse, emergence could explain how universes with vastly different properties arise from the same underlying information. It's a reminder that the multiverse isn't just a collection of separate realities. It's a dynamic, interconnected system where information flows and evolves, creating endless possibilities. So, what happens when information gives rise to entirely new phenomena? How do simple rules lead to the complexity and diversity we see in the multiverse? That's the mystery we'll tackle next, as we dive into the concept of emergence, a puzzle that might just hold the key to understanding how the multiverse comes alive. What if the dazzling complexity of the multiverse, its galaxies, stars, and even life itself, emerges from something as simple as a handful of basic rules? This is the heart of emergence, the idea that intricate patterns and systems can arise from simple, underlying principles. Think of a snowflake. Its intricate, symmetrical design isn't the result of a master blueprint, but rather the outcome of simple interactions between water molecules as they freeze. Now, imagine this principle on a cosmic scale. In the multiverse, entire universes, each with their own unique laws and structures, could emerge from a few fundamental rules, like fractals unfolding endlessly from a single equation. Take fractals, for example. These mesmerizing patterns, found everywhere from the branching of trees to the structure of coastlines, are created by repeating a simple rule over and over. What's astonishing is how complexity arises from such simplicity. A single mathematical formula can generate an infinite variety of shapes, each one unique yet following the same underlying logic. Now apply this idea to the multiverse. What if each universe is like a cosmic fractal, emerging from a simple set of rules that repeat and evolve in endless variations? One universe might spiral into galaxies and stars, while another forms entirely different structures, perhaps even ones we can't yet imagine. But fractals aren't the only example of emergence. Consider self-organizing systems like flocks of birds or schools of fish. These systems don't have a leader directing every movement. Instead, each individual follows a few simple rules, like staying close to a neighbor or avoiding collisions. Yet, from these basic instructions, stunning patterns of collective behavior emerge. In the multiverse, entire realities could self-organize in similar ways, with simple rules governing the interactions of particles, forces, and even space itself. It's as if the multiverse is a cosmic dance, where each universe moves to its own rhythm, yet all follow the same underlying choreography. What's truly fascinating is how these emergent patterns might differ across universes. In one reality, the rules could lead to a universe filled with intricate, fractal-like galaxies. In another, the same rules might produce something entirely different, perhaps a reality where space itself is structured like a giant honeycomb, or where matter organizes into forms we've never seen. The possibilities are as vast as the multiverse itself, offering a glimpse into how complexity can arise from simplicity in ways that are both beautiful and profound. But here's where it gets even more intriguing. If emergence shapes the multiverse, could consciousness itself be an emergent phenomenon? Just as galaxies and stars arise from simple physical laws, could awareness and thought emerge from the intricate interplay of particles and forces? This idea blurs the line between the physical and the mental, suggesting that consciousness might not just be a product of the universe, it could be a fundamental part of its structure. And as we'll explore next, this connection between emergence and consciousness might hold the key to understanding how we, as observers, shape the reality we experience. What if consciousness isn't just a passive observer of the universe, but an active participant in shaping it? This bold idea turns the traditional view of reality on its head, suggesting that our minds might play a crucial role in determining the nature of existence. It's a theory that blurs the line between the observer and the observed, raising profound questions about free will, determinism, and the very fabric of the cosmos. Could consciousness be the key to unlocking the mysteries of the multiverse? And if so, what does that mean for our understanding of reality itself? At the heart of this idea is the concept of participatory reality, a theory that suggests consciousness interacts with the universe in ways we're only beginning to understand. In quantum mechanics, for example, the act of observation seems to influence the behavior of particles, collapsing their wave functions into definite states. This phenomenon, known as the observer effect, has led some scientists to propose that consciousness isn't just a byproduct of the brain, it's a fundamental force that shapes reality. Imagine a universe where every thought, every decision, and every observation creates ripples that extend far beyond our own experience, influencing the structure of the multiverse itself. But if consciousness shapes reality, what does that mean for free will? In a deterministic universe where every event is the inevitable result of prior causes, free will can feel like an illusion. But in a multiverse shaped by consciousness, the story changes. Here, every choice we make could create a new reality, branching off into infinite possibilities. It's as if we're not just passengers on a cosmic journey, but co-pilots steering the course of existence with every decision. This idea doesn't just challenge our understanding of free will, it redefines it, suggesting that our choices matter in ways we can't even imagine. Of course, this raises its own set of questions. If consciousness plays such a pivotal role, what happens when multiple observers interact? Could conflicting observations create competing realities, or do they somehow merge into a single, shared experience? These are questions that push the boundaries of both science and philosophy, forcing us to rethink not just how the universe works, but how we fit into it. As we ponder these ideas, it's worth considering how they connect to the broader mysteries of the multiverse. If consciousness is a fundamental force, could it also be the glue that holds the multiverse together? Could the infinite web of realities be bound not just by physical laws, but by the collective awareness of all conscious beings? It's a thought that invites us to see the multiverse not as a cold, mechanical system, but as a living, evolving entity, one that thrives on the interplay of mind and matter. This leads us to the next chapter of our exploration, the multiverse as a living entity. What if the cosmos isn't just a collection of separate worlds, but a single, interconnected organism, pulsing with energy and awareness? The answers might just change how we see everything from the stars above to the thoughts within. What if the multiverse isn't just a collection of static, disconnected worlds, but a living, breathing entity, a cosmic organism that grows, evolves, and adapts over time? This radical idea pushes the boundaries of how we think about existence, suggesting that the multiverse might not just be, it might live. Imagine the cosmos as a vast, interconnected network, where universes are like cells in a colossal body, each playing a role in a grander system. This isn't just a poetic metaphor, it's a serious scientific and philosophical hypothesis that challenges us to rethink the very nature of reality. At the heart of this idea is the concept of emergence, the phenomenon where complex systems arise from simple interactions. Think of a single ant following basic rules of behavior. Alone, it doesn't accomplish much, but in a colony, ants work together to build intricate nests, forage for food, and even wage wars. The colony becomes something greater than the sum of its parts, a living system with its own intelligence and purpose. Now apply this to the multiverse. What if universes, like ants in a colony, interact in ways that create a larger, living entity? This could mean that the multiverse isn't just a random assortment of realities. It's a dynamic, evolving system with its own rhythms and patterns. Some scientists take this idea even further, suggesting that the multiverse might possess a form of cosmic consciousness. Just as the human brain emerges from the interactions of billions of neurons, the multiverse could emerge from the interplay of countless universes. Physicist Lee Smolin has explored this concept, proposing that universes might reproduce through black holes, creating new realities in a process akin to biological evolution. In this view, the multiverse isn't just alive, it's growing, adapting, and perhaps even learning. It's a vision of the cosmos that's as awe-inspiring as it is unsettling, blurring the line between the physical and the metaphysical. But what does it mean for the multiverse to be alive? If it's a living entity, does it have a purpose? These questions push us into the realm of philosophy, where the implications are just as profound as the science. Philosopher Thomas Nagel has argued that life and consciousness might be fundamental features of the universe, not just accidental byproducts. If he's right, then the multiverse could be more than just a collection of matter and energy. It could be a conscious, purposeful being, driven by forces we're only beginning to understand. This idea doesn't just challenge our understanding of the cosmos, it forces us to confront our place within it. Are we merely passive observers, or are we active participants in a living multiverse? Of course, these ideas aren't without their critics. Some argue that applying concepts like life and consciousness to the multiverse is a stretch, a case of anthropomorphism projecting human traits onto the cosmos. Others point out that these theories are difficult, if not impossible, to test. But even if the multiverse isn't literally alive, the metaphor itself is powerful. It invites us to see the cosmos not as a cold, mechanical system, but as a dynamic, interconnected whole, a reminder that the universe is far stranger and more beautiful than we've ever imagined. As we grapple with these ideas, one question naturally arises: what does the future hold for this living multiverse? Is it destined to expand forever? Or will it eventually collapse, recycle, or transform into something entirely new? These questions lead us to the ultimate fate of the multiverse, a topic as mysterious as it is profound. And as we'll explore next, the answers might just redefine what it means for something to live, die, and be reborn in the cosmic dance of existence. What if the multiverse, with all its infinite possibilities, has an expiration date? Or perhaps no end at all? The ultimate fate of the multiverse is one of the most profound questions in cosmology, and the answers are as varied as the universes themselves. Some theories suggest a cold, dark end, while others paint a picture of eternal growth and renewal. But what does this mean for life, for consciousness, and for the very fabric of existence? Let's dive into the possibilities, from the chilling concept of heat death to the boundless idea of eternal expansion. First, let's explore the concept of heat death, often described as the ultimate fate of our universe and, by extension, the multiverse. Imagine a cosmos where all the stars have burned out, all the galaxies have drifted apart, and all the energy has been evenly distributed. In this scenario, the universe becomes a vast, cold, and lifeless expanse, a state of maximum entropy where nothing happens and nothing ever will. This is the heat death, a slow fade into nothingness. But what if this isn't just the fate of our universe? If the multiverse operates under similar thermodynamic principles, then heat death could be the destiny of all realities, a cosmic stillness that stretches across infinite worlds. It's a haunting thought, one that raises questions about the purpose of existence and the fleeting nature of life. But not all theories paint such a bleak picture. Another possibility is eternal expansion, where the multiverse continues to grow forever, spawning new universes in an endless cycle of creation. Picture a cosmic tree, its branches stretching endlessly into the void, each one a new reality with its own unique laws and possibilities. In this scenario, life and consciousness might not be fleeting. They could persist, evolve, and even flourish in new forms across infinite universes. Some models, like eternal inflation, suggest that the multiverse is constantly birthing new bubble universes, each one a fresh start in an infinite cosmic dance. It's a vision of the multiverse as a living, breathing entity, one that defies the notion of an end. These two fates, heat death and eternal expansion, aren't just theoretical opposites, they represent fundamentally different views of existence. Heat death suggests a finite, closed system where energy is spent and possibilities are exhausted. Eternal expansion, on the other hand, implies an open-ended, infinite system where creativity and renewal are endless. Both ideas have profound implications for life and consciousness. If heat death is inevitable, does that make our existence meaningless, or does it give urgency to the choices we make, knowing that time is finite? Conversely, if the multiverse expands eternally, is life destined to endure in some form somewhere? These questions don't just challenge our understanding of the cosmos, they force us to confront our place within it. But what if the truth lies somewhere in between? Some theories propose a cyclical multiverse where universes are born, expand, collapse, and are reborn in an endless loop. Imagine a cosmic phoenix rising from the ashes of its own destruction, only to begin the cycle anew. In this model, heat death and eternal expansion aren't mutually exclusive, they're part of a larger, cyclical process. Life and consciousness might not be permanent, but they could be recurring, emerging again and again across infinite cycles. It's a vision of the multiverse that balances the finite with the infinite, offering a middle ground between the two extremes. As we ponder these possibilities, one thing becomes clear: the ultimate fate of the multiverse isn't just a scientific question, it's a deeply human one. It's about what it means to exist, to create, and to endure. Whether the multiverse ends in cold stillness, expands endlessly, or cycles through rebirth, the implications for life and consciousness are profound. And as we prepare to wrap up our exploration, these questions will serve as a fitting conclusion to the journey we've taken together. A journey that's not just about understanding the cosmos, but about understanding ourselves. So what have we learned, and where do we go from here? That's the story we'll tell in our final chapter. As we bring this journey through the multiverse to a close, let's take a moment to reflect on the astonishing ideas we've explored. From the many worlds interpretation, where every quantum decision spawns a new reality, to the bubble universe theory, which envisions our cosmos as one of countless bubbles floating in an infinite cosmic sea, the multiverse challenges us to rethink everything we thought we knew about existence. These models aren't just scientific curiosities, they're windows into the profound mysteries of reality, inviting us to question the very fabric of space, time, and even consciousness itself. Science has always been about pushing boundaries, and the multiverse is no exception. It forces us to confront questions that go beyond the limits of traditional physics. What if the laws of nature aren't universal, but vary from universe to universe? What if our existence is just one possibility among infinite others? These aren't just hypothetical musings, they're questions that could reshape our understanding of the cosmos and our place within it. The multiverse doesn't just challenge science, it expands it, opening up new frontiers for exploration and discovery. But the implications of the multiverse go far beyond science. These theories also provoke deep philosophical questions about identity, free will, and the nature of reality. If there are infinite versions of you, each living a different life, what does that mean for the concept of self? Are you still you in a universe where every choice you've ever made played out differently? These questions blur the line between science and philosophy, reminding us that the search for understanding is as much about asking the right questions as it is about finding answers. And then there's the sheer wonder of it all. The multiverse reminds us that the universe or universes are far stranger and more beautiful than we ever imagined. It's a cosmos of endless possibilities where the rules we take for granted might not apply and where the boundaries of reality are constantly being redefined. This isn't just a scientific theory, it's a story, one that invites us to dream bigger, think deeper, and embrace the unknown. As we wrap up, I want to thank you for joining me on this exploration of the multiverse. These ideas are as exciting as they are challenging, and they remind us that the quest for knowledge is a journey we're all on together. I'd love to hear your thoughts. What fascinates you most about the multiverse? Do you think we'll ever find evidence of other universes? Share your ideas in the comments below, and let's keep the conversation going. And as we close this chapter, here's a final thought to carry with you. The multiverse isn't just a collection of alternate realities, it's a testament to the boundless creativity of the cosmos. It reminds us that the universe is far stranger, more complex, and more wonderful than we ever imagined. So, as you go about your day, take a moment to marvel at the infinite possibilities that surround us, because in a multiverse this vast, who knows what wonders might be waiting just beyond the horizon.